All right, in this video, we're going to look through the parent functions for precalculus. We'll start with the constant function and the linear function, sometimes called the identity function, and we'll move into some more complicated ones like the quadratic, cubic, and eventually into things like absolute value and so on. So in this video, I am going to go through each of the parent functions and all of their detail, how to find this information, because all of this information will be stuff that you are expected to either have memorized or know how to find given a given parent function. A lot of this stuff you probably already know, a lot of it will be review, but I am going to treat this like you've never seen it before, so I am going to go into detail about how to find all of these things. At the very least, by the end of these videos, by the end of today, I would expect you to know the names of the parent functions, as I will list. I would expect you to know their equations, which I will fill in here in a second, and then probably most importantly, I would expect you to know how to graph each of them, okay? So a lot of this stuff, while you will be responsible for it come the test, you don't need to know necessarily by today. This may end up being a video that you come back to as you learn how to find these things throughout the unit. But for sure by the end of the day we want to know their names, the equations, and what the graphs looks like, how to graph them from memory, from scratch, without anything to refer to. So the first example is the constant function. And the constant function has an equation of y equals and then a number. So I'll pick any number. I'll pick 0. I could have done y equals 5. I could have done y equals 3. I could have done y equals -1. Even y equals 2.8. I could do, as long as it's y equals a number with no variable, no x, then that's called a constant function. And constant functions are very easy to make a table with. Remember, when you make a table, we're going to plug in some x values and get out some y values. But as we've kind of already talked about, with constant functions, there is no x to plug in a value into. It's always the same y value. No matter what x is, y is 0 in this case. So all of these, remember, represent coordinate points on the graph. So -1, 0 is on the graph, 0, 0 is on the graph, +1, 0 is on the graph, 2, 0. Really, as long as it has a y value of 0, it is on the graph of this function. So this is what the graph of y equals 0 looks like. It is a flat line that goes through the y-axis at 0. If we were to graph the line y equals 2, it would be the same thing, but it would be a flat line that goes through the y-axis at 2. So it might look like this. Okay? Graphing constant functions is generally pretty easy. Okay? In this specific example that we've done, what are the x-intercepts? What are the x-intercepts? Well, the x-intercepts are where it crosses the x-axis, and that's happening everywhere. There are a ton of x-intercepts, infinitely many x-intercepts. Remember, x-intercepts are points on the graph, x comma y. The y value of all of those x-intercepts is 0, and it actually doesn't matter what x is in this case. No matter what number you pick, comma 0, that's an x-intercept of this graph. Remember what this symbol means. That bold typeface R with kind of the two lines is the symbol for all real numbers. The y-intercepts, it says y-intercepts, but functions are only going to have one y-intercept. And that's where it crosses the y-axis, and here, I think we'll all agree, it crosses the y-axis at the point 0, 0. What's the domain of this function? Domain is how wide a function is, or what x values are being used. So this function is infinitely wide from left to right. its domain is all real numbers. Every x value is being used in this function, all real numbers. If the domain is from left to right, how kind of wide is the function, then range is from bottom to top, how tall is the function, or through what y values does the function go through. And the only y value that our function goes through is 0. It doesn't go through any negative y values, nor does it go through any positive y values. It only goes through the one y value of 0. So you could say y equals 0, or you could put it in these fancy braces and say that the set including 0. I would accept both, but y equals 0 is fine. It's the only y value that this function goes through. Okay. Maximum or minimum values. This term extrema means maxes or mins. Okay. And in this specific function, if we ask what's the maximum or what's the minimum, we're basically just asking what's the larger or the highest point and what's the lowest point. But I think you'll agree that in this specific example, there is no highest point or lowest point. In this case, the maximum of this function does not exist, nor does the minimum of this function exist. Remember, DNE is does not exist. Okay. Is this function continuous or discontinuous? This function is continuous. Remember, a continuous function, probably the easiest way to think about whether or not a function is continuous is if you could draw it without picking up your pen or pencil. So pretty easy to draw this. There are no breaks in the graph. We could just draw forever without ever having to jump over something or to go through an asymptote. It's continuous. Is it increasing, decreasing, or constant? Well, boy, I hope that's clear. It is constant. It is not rising, nor is it falling. It is flat. It is constant. Is it even, odd, or neither? This is actually what we're going to call an even function. Let's not maybe worry about why this is an even function today. We'll get to that later in the unit. This is an even function. For those curious, even just means it's symmetrical about the y-axis, and I think we would all agree that if I took this and kind of flipped it up or flipped it over, it would be perfectly symmetrical about that y-axis. If you took this side and reflected it, it would land directly on that. Cool. And then lastly is end behavior. Again, this is something that's not maybe super important for today. It will be important in the coming days, but end behavior is just a way to denote how the graph behaves at the very far right and the very far left. So for this class, when I ask you to write the end behavior, and we're going to get to this in a few days, but I'll ask you to write the following as x, arrow, infinity, y, arrow, and then you'll fill in an answer, and x, arrow, negative infinity, y, arrow, and you'll give an answer. So this right here is how you write end behavior. We would read this as x approaches infinity, y approaches what? And then that's the answer you would give. And as x approaches negative infinity, y approaches what? And that's the answer you would give, right? So the only thing that's ever going to change, depending on the problem, is what number goes here. How you write in behavior is always x arrow infinity, y arrow, fill in the blank. X arrow negative infinity, y arrow, fill in the blank. So the only thing that's changing problem to problem is the number or symbol that goes here, okay? As x approaches infinity, this is a discussion of infinity, so that's way over here on the x-axis, right? Like here's like 6 and 10. Infinity's way over here to the far right. And as x gets further and further to the right, or further and further towards infinity, the y values still sit at a height of 0. They don't go up forever or down forever. They just sit flat forever at a y value of 0. And the same is true going in the negative infinity direction. Negative infinity, way towards the left, the y values are still at a height of 0. Okay? Very cool. Let's do the linear function. We'll go quite a bit faster through a lot of this stuff now that we know what some of these words mean. The linear or identity function has the equation y equals x. So this is our first instance of a variable. We'll make a table. Usually when I'm making tables, I may plug in a couple negative values, a couple positive values, and I'll definitely include 0 just because it's really easy to plug in. And then these are going to give me some points. So it doesn't matter that I'm choosing 2 to -2. I could have chosen any numbers over here, but I'm just trying to get a few so I have an idea of what this thing looks like. You maybe remember. So when x is -2, if I plug that in here, then y is -2. Pretty easy. When x is -1, y equals x. So when I plug that -1 in, I get y equals -1. So this is the case where y is exactly the same as x, or y equals x. So every x value is the same as every y value. Okay? And remember, when you're making a table, what you're secretly doing, you're plugging in numbers in for x, getting out answers for y, and these are giving you points that are on the graph. Okay? So all of these points are on the graph. So -2, -2 is on the graph, -1, -1, 0, 0, 1, 1, 2, 2, and you can probably start to envision what this thing is going to look like. No matter what number you plugged in for x, right? Maybe you plugged in a 10 in for x, then when x was 10, y was 10. So the point 10, 10 was on the graph for every x value. So it's this diagonal line cutting straight through the x and y axis at 0 on a perfect diagonal, on a perfect 45-degree angle. What are the x-intercepts? Remember, x-intercepts are points. This graph only has one x-intercept, the origin, 0, 0. And it has one y-intercept. Again, these are points in space, so the origin, 0, 0. I understand the temptation to say that the y-intercept is 0, but the y-intercept is a point, so it has an x comma y, so 0, 0. The domain of this function, what x values are being used, all of them, right? No matter what x value you look at, it corresponds to a point on the graph. Okay? What's the range of this function? So if domain is from -infinity to +infinity, oh, and I probably should have said this earlier, if you want to write this, if you're more comfortable writing that, these mean the same thing. So I have no preference. But understand, if I write this, I mean this, and vice versa. Cool. So the domain is all real numbers. From -infinity to +infinity, there are no breaks in the graph. It just goes right along. What about the range? The range is from bottom to top, so from -infinity all the way up to +infinity. And it looks like we cover through every y values. The graph is infinitely wide, the domain is all real numbers, but the graph is also infinitely tall, so the range is all real numbers. Nice. What's the maximum or minimum of this graph? Maximum or minimum? This one's actually a bit tricky. It's very tempting to say, and I would probably know what you meant if you said the maximum is infinity. But that's technically not how we're going to say this. Maximum means the highest value, right? This is the tallest point. And no matter which point you said, hey, Mr. Neal, I found the tallest point of this graph, I think we would all agree, well, no you didn't, because no matter what point you claim is the tallest, there's always a higher point, and always a higher point. Because of the fact that it just goes up and up forever, there is no maximum. There is no surefire, guaranteed, quote-unquote, tallest point, because there's always a taller point. Same is true for the minimum value. There is no lowest point. It just goes down forever, so that minimum doesn't exist. This is a continuous function. We could draw that without picking up our pencil. Pretty nice. It is an increasing function. So the other function that we graphed was constant. This one is increasing. How do I know it's increasing? Well, when we talk about increasing, decreasing, or constant, we're always reading left to right and basically answering the question, as I move along this graph from the far left towards the right, am I going up? Am I going down, or am I staying flat? And in this case, clearly, as you follow the graph from the left to the right, you are increasing there. This ends up being an odd function. We won't worry about that. We will fill in the end behavior here, though. Remember, as x approaches infinity, y approaches, and then we'll fill in an answer. As x approaches negative infinity, y approaches, and then we'll fill in an answer. So as x approaches infinity, so when I look at for end behavior, I'm just looking at the far right and the far left. I'm not honestly worried about anything that goes on in the middle. I just want to look at what's going on way out here at positive infinity so way out here, what's the graph doing? And at negative infinity, way out here, what's the graph doing? And as x gets bigger, positive infinity, or as we go further and further and further towards infinity on the x-axis, the y values appear to just get bigger and bigger and bigger as well. The y values are just increasing forever to positive infinity. Same is true as x goes to negative infinity. As x goes way, way out to the left, negative 5, negative 10, negative 1,000, negative 1,000,000, negative infinity, way out there to the left, the graph just goes down forever towards negative infinity. And this would be our end behavior. Okay. We'll pick up with some other parent functions in the next video, probably going quite a bit faster.